All right, here we are with Unit 4, Lesson 4. We're going to start with a warm-up on the mean value theorem here and verify that the mean value theorem does or does not apply to this function on the interval from -1 to 1. So the first thing we want to check is this function continuous? Yes, it is. Because this is a polynomial function, it's just a series of curves, so it is continuous and differentiable. So the first thing I want is, when we're talking about the mean value theorem, we're talking about where does the slope from -1 to 1? What is that slope? And so we're going to find that, and then we're going to look at the derivative of the function to find out where the function has a slope that's equal to the slope from -1 to 1. So here we go. We need, for our slope, we need f of 1 minus f of -1 all over 1, take away -1. So f of 1, if I plug 1 into the function up here, I get f of 1 equals 1 plus 2 plus 4 minus 12. So f of 1 is going to equal, that's going to be 3, 7, 7 minus 5, 7 minus 12 is -5. f of -1, if I plug that into the function, that's going to be -1 minus 2 minus 4 minus 12. So that gives me -3, take away 4 is -7. I think that's -19, at least I hope it is. All right, so I need to plug these guys in. So back to my slope, -5 minus -19 all over 2. So that's going to be -5 plus 19, which is going to give me 14, and 14 over 2 is 7. So because the mean value theorem applies here, that tells me that somewhere in the interval from -1 to 1, I have a tangent line to this original curve, and that tangent line will have a slope of 7. So to find that, we're going to take our tangent line. Actually, first of all, I need the derivative. So we'll do f prime of x equals, this is going to be 5x to the 4th plus 6x squared plus 4. I'm going to set that derivative equal to my slope value of 7, 5x to the 4th plus 6x squared plus 4. I need to subtract 7 off of both sides to get this thing equal to 0. That's 5x to the 4th plus 6x squared, and that's going to be -3. Now, I'm not sure if this thing factors or not, but I kind of don't think it does. And so I'm just going to go to my calculator. I'm going to pop open my graphing calculator here, and we're going to take a look at where this derivative is actually, where this piece of the function is actually equal to 0. So here we go. If I pull up my graphing calculator here, I already have my function typed in here. So here's my y equals key. I've got my function 5x to the 4th plus 6x squared minus 3. When I graph that, I get this function here, and you can see that this function is pretty much a parabola that's centered right at the origin, it looks like. So I need to find both of these values here and here. And so I'm going to go to my second key, calculate. I'm going to calculate number 2 as 0. And I'm going to calculate the 0 on the right-hand side. So I'm going to go up to the left-hand bound, hit enter, go up to the right-hand bound, hit enter again, and you can see the calculator gives me a value of 0.616. And if we do the same thing on the left side over here, we're going to get the same value, only negative. So going back to my function here, I know that x is going to equal 0.616. and x is going to equal -0.616. Okay, so this is mean value theorem here. So there's two parts of this original function. There's two parts, or two tangent lines to the curve at x equals 0.616, -0.616, that have a slope of 7. All right, it says find a value c that satisfies the mean value theorem for f of x equals e to the -2x on the interval from 0 to 3. So again, we're doing the same thing here, so I'm going to need f of 3 minus f of 0 all over 3 minus 0. So f of 3, let's see, we'll do this right up here. That's going to equal e to the -6 power. All right, and f of 0 is going to equal, that's e to the 0, which is 1. All right, so there's my two values there. I'm going to plug those into my slope, and I'm going to have e to the -6 minus 1 all over 3. Now I can't drop that e down to the bottom unless I split this fraction. So I'm just going to leave that as my slope for now. And I'm going to go ahead and find the derivative here. So f prime of x is equal to e to the negative 2x times the derivative of the exponent, which is negative 2. And then I can set my derivative equal to my slope from the left. So if we do that, we get e to the negative 6 minus 1 all over 3 equals negative 2e to the negative 2x. All right, and I want to solve this guy for e here. So how do I want to do this here? I'm going to divide out the negative 2 on both sides. So that's e to the negative 6 minus 1 over negative 6 equals e to the negative 2x. All right. To solve for x, I need to log both sides. So I'll take the log of e to the negative 6 minus 1 over negative 6 equals when I take the log of the right side, when I take the log of e, the negative 2x is going to drop down in front. The log of e is just 1. So this dude here essentially goes away because 1 times negative 2x is negative 2x. And then I can divide this whole thing or multiply. Maybe, you know what, maybe I'll multiply by negative 1/2 here. So I get x equals negative 1/2 times the natural log of e to the negative 6 minus 1 all over negative 6. And if I carefully punch that into my calculator, I get x is approximately equal to 0.897, which does fit in the original interval of 0 to 3. All right? So today what we're going to look at is sketching the derivative of a function and correlate when the derivative is positive and negative to where the function is increasing or decreasing. So we've done some sketching in the past here. It says the graph of f of x is shown below. So this I know is f of x, and they want us to sketch the graph of f prime. Well, wherever f has a min, then my graph goes from decreasing to increasing. So that means my derivative down here, if I look at the derivative at x equals negative 1, 2, 3, 4, I know that the derivative there is going to be 0. So I can graph a 0 on my derivative here. At the maxes, the same thing's going to happen. I've got 0 on the derivative. Here's another min. So I've got 0 at 0, and then at positive 2, I've also got a 0 here. Now, what's happening here is, again, because my function, I'm going to highlight some areas here, is decreasing here, and decreasing here, then my derivative should be negative in those areas. Negative, decreasing, negative, decreasing, negative. And then in the areas where my function is increasing, my derivative should be positive. So positive and positive. And there's a bunch of different graphs that would work for this. This is just one example of what this would look like. So the questions down here are both going to relate to both of the graphs up here. So it says, first of all, give the intervals of which f of x is decreasing. Now, since I've highlighted f of x, that's going to be pretty easy to see. F of x is decreasing from negative infinity all the way up to negative 4. And it's also decreasing from negative 2 to 0. Now these are all yellow highlighted parts. And it's also decreasing from 2 to infinity. Now, while I'm at it, I'm going to answer the question right below it. Give the intervals of which f prime of x is negative. So if you look at the negative intervals for f prime, remember this is f prime right here. And so my negative intervals are all in red here. So I'm going to list all of my negative intervals. Again, that's going to be, look at this, negative infinity to negative 4. That's the first red section there. My second red section is negative 2 to 0. And my third section is 2 to infinity. All right, so you'll notice that those where f of x is decreasing, we know that the derivative is always going to be negative. All right, And we can do the same thing on the right side, give the intervals in which f of x is increasing. That's all of the green highlighted areas up top. So that's going to be -4 to -2 and 0 to +2. And if you look at the question below that, give the intervals in which f prime of x is positive. We have the exact same intervals, -4 to -2 and 0 to 2. All right? So the conclusions that we can make are this. We've talked about this before. If f of x is increasing, then f prime of x is greater than 0. And if f of x is decreasing, then f prime of x is less than 0. Okay? And finally it says, how can you use the information above to know if a point is a max or a min? So again, if I go from, so we've on our graph up here, we've got f decreasing implies, well, I'm just going to say f decreasing. This is f increasing. And so if f goes from decreasing to increasing, then f prime goes from negative to positive. Okay? And so if f goes from decreasing to increasing, then f would have to have a minimum. Okay? So if I can use the information. Okay, so if how do we want to say this? So usually we're going to have information about the derivative. So again, if you look at the derivative goes from negative to positive. Okay, so this is f prime less than 0, f prime greater than 0. So if my derivative goes from negative to positive, then my graph went from decreasing to increasing, which means I've got a min. So if f prime goes from negative to positive, then f of x goes from decreasing to increasing, so f has a min. Okay? And likewise, the reverse is also true, or we could say if f prime goes from positive to negative, then f goes from increasing to decreasing, so f has a max. Okay, and hopefully that's intuitive. If it's not, I would just stop and look at your paper real quick, so we can see that where f prime, so f prime goes from negative to positive at 0. So that means that the function, so we could say that f prime is less than 0, which implies that f is decreasing. F prime over here, f prime is greater than 0, which implies that f is increasing. So if I go from decreasing to increasing, take a look at my graph. Decreasing in yellow, increasing in green, that means that f has a minimum. Okay? All right. I'm going to stop and take a break here for just a second. There we go. Okay, so we've got the first and second derivative shown on the right side here. It says sketch the second derivative on the graph below. So I'm going to have to squeeze down a little bit here, but my second derivative, and I'm going to do this based on the first derivative. So where my first derivative goes from increasing to decreasing, I know that the slope of the first derivative would be 0 here at -3. Also at -1, my first derivative has decreasing to increasing, and then at +1, I would also, so just like we would sketch first to second derivative, we can sketch second to third. So my derivative, the blue graph, goes increasing, which means my second derivative is positive. Then my derivative goes to decreasing, so my second derivative would be negative. Then my derivative from -1 to 1 is increasing, so my second derivative is positive. And then from 1 to infinity, it's decreasing, so my second derivative would be negative. Okay? So that was the first thing we wanted. And then it said, on what intervals is the graph of f of x? So now we're back to f of x, concave up. All right? So concave up means smiling. So where's the graph smiling? So I'm going to trace these parts on my graph. My graph is smiling from there to there. It also looks like it's semi-smiling from here to here. And then where is it frowning? Where is it concave down? Okay, so I'm going to highlight those areas as well, concave down. So this is a frown when we talk about concave down. Okay, so I've got two areas where I'm concave up and two areas where I'm concave down, and they want the intervals for each one of those. So my first one, concave up, smiling, that would be from -infinity all the way over to -3. So -infinity, comma, -3. And it was also smiling or concave up from -1 to 1. And then where was it? On what intervals? Oh, you know what? I got these in the wrong spot. Concave up. Let me go back. I wrote these in the wrong spot. -infinity to -3, smiling, and -1 to 1. Okay. All right. And then where is my graph concave down? So I'm looking at the frowning part, so that would be -3 to -1. I'm frowning. And +1 to infinity. All right. And then it asked me about the second derivative, on what intervals is the graph of f prime of x positive. So I'm going to mark some positive intervals. So f prime of x is positive here, and it's also positive here. And then it asked me to mark where it's negative. Okay, and it actually doesn't ask me to mark this, but I'm marking this so you can, oops, let me do this. I didn't want that color. I actually wanted blue here. So negative here and negative there. Because what they're asking for now, again, is on what intervals is the graph of f double prime positive. If you look at the positive intervals, that's like areas highlighted in yellow here. So f double prime is positive from -infinity to -3, as well as -1 to +1. Now look at the answer right above this. -1 to +1, same exact answer. Okay, look at the second one as well. Where is f double prime negative? That would be -3 to -1, as well as 1 to infinity. The graph of f double prime is negative. It matches the intervals right above there. So conclusions that we can make here, we can definitely say that if f double prime is greater than 0, then f is concave, oops, I'm going to write this out the first time, concave up. Okay, so if my derivative, the highlighted yellow parts, is greater than 0, then my graph of f of x is concave up. If f double prime is less than 0, then f is concave down. Okay, so the second derivative will tell us something about the graph of f. Okay. Now, if you take a look at the table down here, it says that the number line has data we collected on the first derivative. So if you'll notice the number line here, I'm going to make some marks on here as well. So if you look at my number line here, it says that f prime is negative from negative infinity to negative 4. So if you go look at the graph of f prime, it's definitely negative from negative infinity all the way up to negative 4, and you can see that mark on the graph right there at negative 4. And then it goes to positive until negative 2, and then it goes to negative until 0, and then it goes positive to 2, and then it's back to negative at 2 to infinity, so everywhere on. So these are the intervals in which f prime is negative, positive, negative, positive, negative, and you will notice that f of x on those same intervals, f of x is decreasing until negative 4, then it's increasing until negative 2, it's decreasing until 0, and it's increasing until positive 2. Just like a derivative and a function, just like the things that we've talked about already. What they want us to do here is fill in the information for f double prime of x. So when I look at f double prime of x, we said that f double prime was positive from negative infinity all the way up to negative 3 here. So I'm going to use a different color here. So we're going to go, what color do I want to use here? We'll go purple. So negative infinity to negative 3, we said that f double prime was positive. And then from negative 3 to negative 1, f double prime was negative. From negative 1 to positive 1, f double prime was positive. And from 1 to infinity, f double prime was negative. And what that told us was where f of x was concave up and down. So if I mark off these same intervals, negative 3, negative 1, and positive 1, when f double prime was positive, our graph was concave up. So concave up at negative 1 to 1. And where f double prime was negative, our graph was concave down. Okay, so those intervals go hand in hand, just like derivative and the first function. Wherever the derivative is negative, the first function is decreasing. And the same thing, where my second derivative is negative, my function is concave down. Okay? So, using the data from our little number line tables up here on what intervals is the graph of f both increasing and concave up. Increasing and concave up. So I'm increasing in this section here, and I'm also concave up in that section there. And then I'm increasing from 0 to 1 and concave up from 0 to 1. So I could definitely put those in there. So I would have negative 4 to negative 3 and 0 to positive 1. Decreasing and concave down. Okay, so I got to be careful here. I need a good color here. We'll just use yellow. Decreasing and concave down. So where is f decreasing? So negative 2 to negative 1. Negative 2 to negative 1, decreasing, concave down. And 2 to infinity, decreasing, concave down. All right, so we would have negative 2 to negative 1 and 2 to infinity. Okay, now the last part says the point where a graph goes from concave up to concave, goes from concave down to concave up, or concave up to concave down, is called a point of inflection. So if you look at my original graph here, these points that I marked off earlier, or in between the highlighted sections, these guys are called points of inflection. Okay, point of inflection. It's where my graph changes from concave up to concave down, or vice versa. If you go down and look at the second derivative and look at those same values of x, so I've got x equals negative 3, negative 1, and 1. Look at those values on the second derivative, negative 3, 1, and negative 1 and 1. Those are my x-intercepts on my second derivative. Okay, so the coordinates here, x equals -3, -1, and 1. So those are the coordinates, the x coordinates of each point of inflection. How could you find these same x values from the second derivative? Okay, to find a point of inflection okay, we want to find where f double prime is equal to 0. Okay, not too bad, is it? All right, time for another break. I need some more to drink here. All right, here we go. Another example similar to the other one. So we're going to start off by sketching the second derivative. Again, the second derivative is based on the first derivative, so I'm going to look for my mins and maxes on the first derivative. I've got 3 of those, which means I'm going to have 3 x-intercepts here. 1, 2, 1 at -3, 1 at -1, and 1 at +2. F prime of x is decreasing, which means my second derivative is going to be negative. Then it goes to increasing, so my second derivative is positive. Then back to decreasing, so I'm negative. And then it's increasing, so I'm positive until infinity. So there's my second derivative. It says on what intervals is a graph of f of x, concave up and concave down. So I'm going to highlight those again. Concave up is smiling. I'm going to highlight concave up in yellow. So I'm smiling. It looks like here and maybe here. And I'm frowning concave down in these intervals here, here, and that's it. Okay, so concave up, smiling. Looks like we're at -1 to -3, all the way up to -1, as well as 2 to infinity. And while I'm at it, I'm going to look at the question below on what intervals is the graph of f double prime of x positive. So I need the places where f double prime is positive. Look at this, -3 to -1 and 2 to infinity. Same intervals that we just looked at, -3 to -1 and 2 to infinity. All right, concave down, we're -infinity to -3, -infinity to -3, and we are -1 to 2, -1 to 2, and if I go to my second derivative graph, on what intervals is the graph of f double prime negative? I'm negative here, and I'm negative here from -1 to 2. So we're going to have -infinity to -3, and we're going to be negative second derivative on -1 to 2. All right, so the conclusions I hope are, somewhat obvious here. Okay, if f double prime is, we'll start off with positive greater than 0, then f is concave up. If f double prime is less than 0, oops, I forgot the n, then f is concave down. All right, so just like the last one, okay, this time we're going to fill in all the information from the graphs on the number lines themselves here. So first thing we're going to talk about is f prime of x. So I want to know what's happening with f prime of x. Where is it positive versus negative? So positive, I know, is, let's see, and I'll do a little bit of highlighting for positive here. So we're positive here, we're positive here, and we're positive here. That might make it a little bit easier to see. So I'm positive from -infinity up to 1, 2, 3, 4, up to -4. So positive. And then I'm also positive from negative 2 to 0. So negative 2 to 0, I'm positive. And then I'm positive from 1, 2, 3, 4 to infinity. Positive. All the other sections in here are going to be negative. Negative from negative 4 to negative 2, negative from 0 to 4. And you can see based on the graph, I'm definitely negative from 0 to 4 there. So what does that tell me about f of x? Well, if you look at f of x on each one of those intervals, if you think about what we've talked about in terms of f of x, from negative infinity to negative 4, here's negative 4 on the graph of f of x, I'm increasing. And then from, negative 2 to 0, let's see here, negative 2 to 0, here's negative 2. I'm increasing on that interval as well. So this hopefully makes sense with what we've talked about with our derivative before. If the derivative is positive, f is increasing. So I'm increasing from negative 2 to 0, and I'm also increasing from 4 to infinity, which means I'm decreasing on these other intervals. Okay? And f double prime, I want to know where f double prime is positive versus negative. So I'll do this one in a different color here. F double prime is negative from negative infinity all the way up to negative 3. So f double prime was negative. It was also negative from negative 1 to 2. So negative in this section. And it was positive in these other intervals. Positive from 2 to infinity. So what does that tell us about f of x? If f double prime is negative, then that means that f of x is concave down. So I'm concave down also from negative 1 to 2, concave down, which means I'm concave up from negative 3 to negative 1, and from 2 to infinity. Okay? All right. It says, on what intervals is the graph of f both increasing and concave up? Let's look at that again. Increasing and concave up. So I need to look at f, concave up and increasing. Okay, so I see f is increasing from negative 2 to negative 1, and I'm also concave up from negative 2 to negative 1. And then I'm increasing from 4 to infinity, and I'm concave up from 4 to infinity. So I'm increasing and concave up on negative 2 to negative 1, and I'm increasing and concave up on 4 to infinity. Okay? So if we look at those intervals on f of x, negative 2 to negative 1. Okay, so I'm going to do a little bit of erasing here. So if I look at just negative 2 to negative 1, look at what's happening in here. Negative 2 to negative 1. Negative 2, that's negative 2. I'm increasing. Did I do that right? Negative is, concave up, negative 2 to negative 1. Oh, I'm looking at the derivative graph here. Oops, wrong graph. I knew something looked funny there. Okay, negative 2 to negative 1. Here we go. That looks better. Negative 2 to negative 1. I'm increasing, and I'm concave up right there. Okay? And the point where I stop being concave up at x equals negative 1, that is a point of inflection. Okay? So, where am I both decreasing and concave down? Let's do that. Decreasing, concave down. That's decreasing from negative 4 to negative 3, concave down, negative 4 to negative 3. Concave down, 0 to 2, and decreasing 0 to 2, both of those, and I think that's it for concave down. So we've got the interval from -4 to -3, where we're decreasing in concave down, and 0 to 2, decreasing concave down. All right? The point where a graph goes from concave down to concave up, or concave up to concave down, is called a point of inflection. In other words, where we change from a definitive concave up to a definitive concave down, that point right there is a point of inflection. Okay? A POI is a point of inflection. So we have 3 points of inflection, x equals, and again I'm going to go back up to f for a minute. I'm changing concavity at -3, at -1, and at +2. So -3, -1, +2. X equals -3, -1, and +2. If you look at your second derivative, look at the x-intercepts on the second derivative. -3, -1, and +2. How do you find these same x values from the second derivative? We're going to, let me do this, we're going to find f double prime of x and set f double prime equal to 0. It's basically the same thing I said on the last page, just a little different way to say it. Okay? All right, break time again. All right, here we go. So this time we're going to try and work a little bit in reverse here. We're going to try and put a graph together based on some information about the first and second derivative. And so the first thing we look at here is we see that f prime of x is negative, and that's going from -infinity to -1. Well, what does that tell me about f of x? That tells me that f of x is decreasing. And then I go, f prime goes to negative up until 0. Oh, so hang on a second here. I need to back up just a second here. It looks like, whoops, it looks like f prime of x was negative all the way up until 0. I'm not sure why I wrote this twice on either side there, so that threw me off a little bit. Okay, so if f prime of x is negative, then we know that f is decreasing from -infinity to 0. And then f prime goes to positive from 0 to infinity, which means f of x is increasing from 0 to infinity. Okay? And then we go down to our second derivative, and our second derivative says that f double prime of x, I'm going to do some more lines here, f double prime of x is negative from -infinity to -1, which means that f is going to be concave down in that interval from -infinity to -1, and then f double prime stays positive all the way up until 1, which means that my graph is going to be concave up from -1 to 1, and then f double prime goes back to negative, so my graph goes back to concave down. Okay, so that's just like the information that we had on the last 2 pages. And then on the right side here, we've got some information about different things here. We've got f of -1 equals 3/4. So if I go over here to -1, do a little bit of sketching here, -1, 1, 2, 3, -1, 3/4 looks like it's here. So we've got that guy done. F double prime of -1 equal to 0. This tells us we have a point of inflection at -1. So that point that we just graphed is a point of inflection. F of 0 is equal to 0. So that's right here at the origin. F of 0 equal to 0. So this is going to be the graph of f of x. Keep that in mind. F double prime of 0 equal to 0. That means that our derivative is equal to 0 at that point. So let's see what else is going on here. Okay, I'm going to skip that one for a minute. We've got this guy here. We go to f of 1 equals 3/4, so that would be right about here. And then we're told that f double prime of 1 is equal to 0, so we have another point of inflection right there, which means my graph should be changing concavity at -1 and +1. And you can see that from our chart right above the graph, at -1 we go double prime, f double prime goes from negative to positive, and then positive to negative at 1, which indicates a point of inflection. Now, let's go ahead and try and sketch this, and we'll talk about what's going on. So I'm concave down up until -1. So concave down might be something like that. Boy, that's a horrible picture there. Let's try that again. Concave down. And then from -1 to 1, I'm concave up, and I have to hit 0, 0. So let's see how well I can do this. Concave up. Okay. So I'm concave up from -1 to 1. And then I'm concave down after that again, so I'm changing concavity. Wow, this is tough to draw on today. There we go, that's close enough, all right? Now if we go back and look at this last point, it said this last point, f prime of 0 was equal to 0, basically telling me that my graph went from decreasing, you can see on the graph, I went from decreasing to increasing at x equals 0. Okay, so if f prime of x is 0, then I should see a minimum or a maximum on the graph of f of x, and we've got a min right here. Okay? All right, let's check out another one here, see what we got going. So same thing, we've got some number line information. It looks this time, we've got f of prime of x is negative up until +3. So that means that f of x is going to be decreasing. And then we're positive from 3 to infinity, which means I'm increasing. And f double prime starts out negative up until 1, which means that f of x is concave down. Then we go positive, positive again. Interesting. So this is going to be f double, or f prime is positive from 1 to 5, which means I'm concave up. And then we go back to f double prime negative, which means I'm concave down. All right. Okay. So now that we have our chart filled in up top here, we can go ahead and look at the graph of this. On the top here, I do need to make one correction. F of 3 is actually supposed to equal -4 here. Okay. So we know that f of 1 is equal to 0, so I'm going to plot that. I'm told that f of 3 equals -4, 1, 2, 3, 4. And that f of 5 is equal to 0. So I've got these 3 points on the graph of f. Those guys are good. I'm told that f prime of 3 is equal to 0. And so if you look at the graph of f of x, notice from 1 to 5, I'm concave up. And I go from, again, if you look at the blue up top, I go from decreasing to increasing in that interval, -1 to 5. So if I draw that graph decreasing to increasing, that would definitely say that f prime of 3 is equal to 0. But this is about to get a little bit trickier because it says at f prime of 1, I am undefined. At f double prime of 1, I'm undefined. At f prime of 5 and double prime of 5, I'm undefined. Now, that means that I either have to have some sort of a sharp turn or cusp. So if my first derivative is not defined, then I have to have a sharp turn or cusp. Or I must not be continuous. So if we look at the rest of the information here, there's nothing in here about a vertical asymptote. Okay, so I don't know anything about vertical asymptotes because I am defined at 1 and 5. And if you look at f prime of x, I'm decreasing from -infinity to 3, decreasing, and I'm concave down from -infinity to 1. Now, normally if I were to draw this, I would draw a concave down from -infinity to 1 like this, but then the derivative at 1 would exist. So on this particular graph, we're going to have to be concave down, but I'm going to say that we're where's my pen? Can't get a pen. I'm going to say that we're concave down, but we must be not continuous. Somewhere in that interval, somewhere around 1, something funky is going on here. And the only way I can keep this graph concave down and decreasing, so the orange part of my graph is concave down and decreasing, and the green part is now concave up from 1 to 3. You can see that it's concave up in the chart, and I'm still decreasing from 1 to 3, and then I go back to concave up from 3 to 5. I'm increasing from 3 to infinity, but at 5 I go back to concave down, and the derivative at 5 is undefined. So I must have something weird going on like that that would make my first and second derivative undefined. Okay? Hopefully that made sense, and have fun with the assignment tonight.